No. All right, day 3 of this e-learning stuff. Today we're going to focus on these identities again, but actually doing what's called verifying an identity, which we have already done. So you'll have these in front of you, and hopefully have that accessible as you look at the homework, and then you know what verifying an identity is. The answer's right in front of you. Okay, so this is from 5-4, and then the homework, I pull 3 questions from the quiz section on page, I got it right here, page 232, which is on that calendar thing there. Just some good questions that I think are quite doable. All right, so you know what the structure of an identity is. It's the answer is right in front of you. All right, and so that's what's great about this. We know where we're trying to go. We're trying to go here, and I think you would agree that the left side is much more complicated than the right. Now, in my class, I just want structure going down like a geometry proof. I know in some of the other classes, you might be writing your reasons off to the side while you make these substitutions in, but I just want a logical step from one to the next. And some of you need to really work on that in my class. Like I made the notes very specific. Step them out, and then each line is equal to the previous line. So you make your substitutions and you make them all. All right. So the first thing is, all right, you do something, not nothing, right? I always say that in my class as well. And I look at that and say, okay, I just learned the sum rule for sine. And I think that's what they're trying to make me to do. Because when I look at this side, I just have a 2 sine x cosine y. So I'll use the sum rule first. And the sum rule for sine is sine x cosine y, sine, same sign, plus, and then I just like doing it this way, sine y cosine x. That is the sum rule for sine, so I'm going to do something. Identities say, all right, I do these substitutions, I see what happens, and then do I come down to something that equals the right side? Plus, then this, I go ahead and look at my difference rule for sine. Good, that looks like a good size there. And the difference rule for sine is sine x cosine y. Sine, the sign is the same. Sine y cosine x. And then for my class, I just say put the equal sign. You don't have to keep writing the right side. When we're done, we just arrow down. Yes, the left side turned into the right side. And then your logical steps. Everything looks good. This does equal that. This does equal that. This whole line does equal that whole line up there. There's nothing missing. All right, some of you need to work on this structure. We cannot have sloppiness. Sloppiness will be marked wrong. All right. Okay, well then when we look at this, you have to understand that this is 1 term, 2 terms, 3 terms, 4 terms. You cannot take this sine of x, or let's say you can't take this sine of y and cancel it with that sine of y. But when you look at this, these are exactly the same, except one's a minus and one's a plus. So this is like having xy, I'll use a different variable, pq. That's a q? What the heck was that? That's page. PQ minus PQ. Mind your P's and Q's, by the way. Subtract, then those would actually cancel as 2 complete terms. I can't really think of another way of writing this, to get you to understand that. This whole thing is exactly the same as this whole thing, but they're opposites, so they completely and totally subtract each other out. And then doing the idea of common terms, this is like, again, I'm trying to, QZ plus QZ. I just want different letters here. QZ, I can't write my letters right here. That's 2 QZs. That's simple adding like terms ideas. And that's what, we have troubles, I guess, in this stuff, understanding that this trig is working like variables. Anywho, step number 2, we're done. 2 sine x cosine y, that's how easy these are, equals 2 sine x cosine y, check baby, 1, 2, 3. And that's what verifying an identity is. Let's move on. You can always pause the video and relook at that. You do something, not what? Nothing. So the sine sum rule. Step 1, sine 210. Oh, I love this question. Cosine x. That's what the sine sum rule is. That's why I got these right here. Sine sum rule. Sine of a plus b, sine a cosine b, plus sine b cosine a. I just decided to write it like that because multiplication is commutative. All right, plus sine x cosine 120. And then for the purposes of highlighting, you don't have to highlight in your homework. I took care of this. Now, this is a big one. Minus parenthesis. Whatever I write out of this, whatever this becomes from the cosine rule, you have to subtract all of it. So it must be distributed, the minus sign. All right, and then cosine is cosine, cosine. Go look up at the rule. Cosine, cosine. And then cosine, the signs are different. Sine, sine. I ran over this line here. I wanted to fit this in. Oh, well. Sine of x. And then for my class, we put equals, and then you probably could write 0, but we're trying to get this to equal 0, and we're seeing if that actually happens. Okay, then what we need to do, well, this one we actually have to evaluate sine of 210 and cosine of 120 for both of these. All right. Oh, I did a little switcheroo. My bad, dogs. Rough. I looked at the other one, and then I did a little, what do you call that? Dyslexia. All right. A little switch of the numbers, which I do sometimes in class. Okay. So, sorry, that's a 210 there. So we have to actually evaluate. And what's 210? And maybe in these, does the work belong like logically in this structure? And in the past, I have let students like put that there, or it could be up here. But really, in theory, you should be able to think, have the mind calculate, know what 210 is. It's a 30 in quadrant 3. Sine is negative in quadrant 3. And sine of a 30 is a half. You do whatever you need to do to get that figured out. That's the next thing that should be in your logic structure of this identity. Again, there's no snaked work. There's no secret work off to the side. Each step logically is equal to the previous one as you evaluate. And then cosine of a 30 is actually root 3 over 2. And you probably should write that in front of this sign. And then you must understand that these are now terms with coefficients in front of them. And that's how we have to look at that. We're going to go ahead and maybe let's handle the distribution as a separate step. But I know this is going to be a little bit lower or shorter in writing. Cosine of 120, that's a 60 in quadrant 2. Cosine of a 60 is negative a half. And then that's cosine of x. 60 in quadrant 2. 60 is root 3 here. Negative 1 and 2. And then feel free to divide by 2 for you unit circle people. We're like in the transition of that there. But minus, and then sine of 120 is actually positive root 3 over 2. Sine of x. Equals. Then the next step, we're going to go ahead and negative 1 half x cosine x. You can make that negative or minus or plus a negative. It doesn't matter. Then we're going to go ahead and distribute the minus sign. And then we're going to see how this all takes care of itself. That makes this plus root 3 over 2 sine of x. So now we see what happens. You're gone. You're gone. And this is how it always ends. Something equals itself. You do write that last step. Prove it. Check baby, 1, 2, 3. Everything is logical building up to that. So you do something, not, and I think these are very doable. If you just use those identities as given. All right. I think I only have 2 more. Then there was one that I really liked that is not as hard as it actually looks. Okay, so again, do something, not what? Nothing. Okay, do something, not nothing. Okay, this one does tend to be a weird one. We look at the right side. Obviously, this is less complicated, so we're going to be working with the left side. And you should say to yourself, okay, well, I can at least do this. This is the rule where, I just learned. It's the sum rule for sine. So if I do something with that, let's just do that and then see what happens. And the sine sum rule is sine of s, cosine of t. I hate s's and t's for variables. Sine plus, sine is the same. And then I just like making it, I say this a million times, sine t cosine s, cos, over. Now this is where the stuff hits the fan, so to speak, when rules of math go out the window. If you do this, pew pew, pew pew. First of all, look at the right side. Someone that does that, is that what the right side looks like? Is that what the answer is? No. As a Fermat, this is another 6 over 5 equals 2 error. You can never, ever take part of a sum and cancel it with another factor on the bottom, because what you end up with is invalid math. This is not true. 6 over 5 does not equal 2. That is why we can't do that. That is exactly why we cannot do that. Variables and trig and numbers, they're all follow the same rules, I guess is what we could say for that. What was that? Cos? Yes. All right, so get rid of that. No, 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 no. Can you do that? But what you can do is that weird thing that we've done in the past. I look at this and I have a big fat plus sign, no big fraction. So I'm going to do the reverse of the common denominator rule. That's what I call it. Because usually you get a common denominator and you put them under or over the common denominator. Well, that means you can reverse it and separate this into two separate fractions. And now that's where that big plus sign comes in with these here. Oh, I see where this is going now. And hopefully you do as well. Cos over cos. I got all excited about those S's and I wrote an S. Now equals, wrong, equals 2, step 2. Make sure you show your steps so I can see your logic. Right, and I want to keep showing this one. Well now, okay. Well now these are separated fractions that I can cancel the things that are exactly the same. Now that's a much different thing. Boom, boom, nice. So what's sine of s over cosine of s? Well, by golly, I think that's tan of s by definition. Plus, and then what's sine of t over cosine? Well, by golly, I think that's tan of t. And by golly, when I look at the right side, that's exactly what the right side is. Check, baby. Anyone? Check, baby. 1, 2, 3. Done. That's why I like to. Oh, no. I was scared to actually use this as an example. I'm going to check my time here, too. All right, 13 minutes. That ain't bad. Okay. Oh, this one's. Okay, here we go. Here's the tan rule. Do something, not nothing. The tan rule is tan x, tan y, subtract on the top, over 1 plus tan x, tan y. So don't freak out over it. Just do your replacements. Take each thing one step at a time. All right, but then remember the structure. This is step 1, and we keep going. Minus, and then I'm going to do this. And then there might have to be some distribution. We'll see how that shakes out. Well, yeah. Okay, and this is going to be great. You're going to love it. This is tan y minus tan x. Oh, this is going to be so simple. I could see where this is going. I don't know why I was afraid of this one. Over 1 plus tan y tan x. So it looked scary at first, but now when I look at this, I am subtracting two things that already have anyone, a common denominator. So I'm going to purposely write this as a extra step that probably will not be needed in your part. But the purpose of it, and then look at this. Tan x, tan y, is that any different than tan y, tan x? No. Multiplication is commutative, and you don't have to show that as a step, showing it's commutative, so these are the same. No, there are certain things that, in this high-level math class we can surmise, This is what I mean about writing this like this. You probably could have went ahead and distributed the minus sign. But I'm going to write this like this, and making you understand that when you subtract this numerator, it does have to be distributed. This is the biggest mistake ever made, not distributing a minus sign to this minus sign. Over one common denominator, because look at the right side. I already have accomplished the denominator in this, trying to verify this identity. And then when I distribute this minus sign, then you may figure this out. Okay, this is what's strange. I have a tan x and a tan x. This again is probably writing this too much. That's 2 tan x. And then I have a minus tan y and a minus tan y, which is minus 2 tan y's. All right, I got to zoom this in so we can see all of this here. Over the common denominator, 1 plus tan x, tan y. And then the only thing you have to do to verify this completely is take out the 2's factoring equals. So maybe 3 steps if we went ahead and distributed the minus sign up here. It gets a little touchy, like what teacher wants what. So I think this is pretty good as far as being thorough. I always demand that the last statement is exactly what the other side equals, is what you write. You don't short change that. Tan y equals, and I gotta zoom this back in here. Darn tootin'. Verified. And I love this last one. This one's like, oh, I looked at this and I'm like, boy, that looks really challenging. Do I have to put the tan rule here, which is a fraction within a fraction? And then within here, I have to put the same tan rule, which is tan alpha plus tan beta over 1 minus tan alpha tan beta. But then I'm like, wait a minute. Watch this. Maybe you got it too as well, how this ended up being so easy. This looks like this. Tan A plus tan B. I'm just putting a thought bubble up here. Over 1. Oh, wrong. I knew something was wrong when I saw that plus sign on the bottom. Minus tan B. So it's minus up there. Over 1 plus tan A tan B. So you wouldn't have to write this. It depends on the teacher. I just like the logic. If you can see that that is actually working like A, and that is working like B as the the thing in the formula. I can't think of the word. I'm trying to think of a math word, but I'm losing it right now. So what does this equal? This equals the rule tan A minus B. So actually what I'm going to do for step number 1 is write that in this form, where A is alpha plus B, and B happens to be beta. Holy crap. And then step 2, you're done. You proved it. So it was a lot easier than it looks. That was crazy. Okay, so anyway, give you some ideas about how verifying identities go. I think all of the math teachers want this structure. Some require that you write reasonings off to the side. So you take note of that. At least this gets you something here, okay? All right.